will deal with MVP magnetic vehicular positioning system for GNSS-denied environments. During the last 2 decades, there has been a rapid growth of navigation systems since GPS popularity. The navigation system has become an integral part of our lives. Let me do a quick survey. Do you drive? Have you ever misled by a navigation system before? And I believe most drivers have encountered the following situation. We miss the ramp that the navigation system asks us to go up. However, the navigation system still keeps navigating, and it took us to the wrong place. We feel betrayed and didn't want to trust the navigation system anymore. This is not the best solution. So the purpose of my research is make navigation system trustworthy in every environment. As you can see in this slide, GPS is one of the global navigation satellite systems. Why is GNSS not usable in some environments? Because the GNSS signal is easily blocked by steel, concrete, and even some kind of glasses. Then, when we are driving in a tunnel, as we know, it's made from concrete and steel. It is impossible for us to receive GNSS signals, which means we could not use the navigation system. Since this is an important issue, there are many techniques that attempt to solve this problem. We analyze this technology based on how accurate and expensive they are. For example, LiDAR offers the highest accuracy, but the cost of making an accurate 3D map is expensive. And LiDAR itself is expensive also. Beacon, which has been commercialized, on the other hand, costs less than LiDAR. However, it can only reach the accuracy of about 20 meters. So our goal is to develop a technology that can reach better accuracy and is relatively inexpensive and can be implemented on a smartphone. Once, we recorded 4G signals on a bridge. We found out that there is a small magnetic field interference. Then, we realized this interference can be used for positioning. So, where do the magnetic fingerprints come from? Originally, the geomagnetic fields are homogeneous. However, we want to shorten the traveling time, so we build a tunnel. And the iron inside the tunnel will twist the magnetic field due to the heterogeneous of permeability. Then, since the distribution of iron in each tunnel is unique, every tunnel has unique magnetic fingerprints. So, how to positioning with magnetic fingerprints? When the driver enters the data loading area, the system will load the magnetic field map, which we show here as red line. The system will further convert this information into, then after entering the tunnel, the MVP will determine driver's lane. Once the lane is identified, the system will start positioning by aligning the two magnetic field sequences. This way, we can find out how far the driver is from the entrance. And the system will further convert this information into geographic coordinates. Now, we know we can positioning by magnetic fingerprints. However, how can we make this kind of map? In the beginning, we made a magnetic field map by cruise control. The idea is simple. We set the car at steady speed And it will record the magnetic field in the equal space theoretically. That's it. As we repeat this process in each lane, we get the magnetic field map. However, things are not always so perfect, so do the cruise control. Even if the speed can stay steady, the car in the lane will shift near left or near right. This phenomenon causes errors. We need a better solution. We turn our eyes upward. The light is equally spaced and bulging. If we could detect those lights, we can make better map. Therefore, we use a LiDAR to scan the ceiling. As we detect the light, we could know where we are by those lights. Then, we could make a map, which is way more accurate than before. For the next issue, let's talk about the delay. According to our finding, short measured data provides short delay but low accuracy. On the contrary, long measured data provide high accuracy but long delay. Getting high accuracy is good, but the problem is that long delay can decrease accuracy. The driver cannot be positioned when they encounter a delay. We need a faster algorithm to fix this. So, we decide to make a combination of machine learning and dynamic time warping. In the beginning, we use CNN for lane determination and rough positioning with a short sequence. Then, we set the result as middle point and expand the range gamma to cut a piece of map. Finally, we use the same sequence to align the map pieces for precise positioning. This way, the accuracy will remain while the delay will be shorter, which means we can have a better accuracy. Next, we want to know what impacts MVP. There are many variables that may affect our method, such as sensors, time, type of vehicle, surrounding vehicles, and the electronic devices. However, after we did the experiment, we found out that only the electronic devices will significantly affect our system. Now, let's look closely how that works. We tested on speaker, dashboard, screen, charger, wiper, and air conditioner in terms of a minimum unaffected distance. Besides, we measure the general distance of smartphones and those devices based on smartphone placed in front of central control, as we show here. We can see that all devices' general distance is bigger than minimum unaffected distance. That is, these devices will not affect MVP in general conditions. Therefore, we set the measured data length as 3 seconds and the expanded range as twice of measured data length. We did a large-scale road test. In most of the tunnel in Taiwan and some really famous bridges in San Francisco, the duration of this test is 30 months. Moreover, we collect 5,943 data sets in total. The type of tunnel will affect the accuracy. Overall, we had the best accuracy in rock shades and the worst accuracy in boring tunnels. The lane determination accuracy in cut and cover tunnels that we test is not applicable because there only has one lane in each direction. But overall, the lane determination accuracy can be higher than 99%. On the other hand, we have the best accuracy in suspension bridges, while the worst accuracy is simply separated bridges. In addition, the accuracy of lane determination can reach 100%. Now, here's a question. Why does MVP perform differently for different types of buildings? because the homogeneity and the amount of steel structure is varied, which leads to the diversity of magnetic fingerprints. That is, MVP works better in fingerprint with unique feature than the homogeneous fingerprint. For example, the Golden Gate Bridge uses a lot of steel, and it has inconsistent cables to handle bridge. Therefore, it has a unique fingerprint, which is easy for MVP to position. To conclude our study, our method can reach nearly 100% accuracy in lane determination and 3.9 to 7.6 meter accuracy in positioning. And it can be used in any orientation, in any weather, and no infrastructure needed, no accessory needed. And it can be run in a smartphone. Thank you.